All right, so the next screencast for nuclear chemistry is going to talk about half-life and what half-life is in terms of radioactive elements and what we use half-life for. So first of all, what is half-life? It's the time required for 1/2 of a given quantity of a substance to undergo change. So it's how long it takes for alpha decay or for beta decay to happen for half of a sample. Some elements decay very quickly, some elements decay very slowly through alpha decay or beta decay. So it's just basically how long it takes. So each radioactive isotope has its own half-life, and we can actually use this to determine the age of things. It ranges from a fraction of a second to a billion years. So depending upon what radioactive element you're looking at, when we talk about those transmutations reactions of them going through alpha decay or beta decay, the time that it takes varies. So here's a table showing some, kind of common half-lives or some common radioactive elements with their half-life. So carbon-14, that's the one we use for dating, radiocarbon dating. It's 5,730 years. So for carbon-14 to go through beta decay, it takes 5,730 years for half of a sample to decay. So if I had 100 grams, it would take 50, or for it to become 50 grams to decay, to go through beta decay, and half of it to decay away would take 5,730 years. Cobalt-60 takes 5.3 years. Hydrogen-3 takes 12.3. And then there's, some of them like uranium-235 is 710 million years. So some take a long time, some don't take very long at all. So basically you can graph the half-life and you can see that you never end up at 0. You just keep cutting it in half, cutting it in half, and cutting it in half. You never actually will end up at 0. But a half-life is how long it takes for half of a sample to break down. And when you just look at the amounts, so even if I'm starting with, an odd numbered amount, I can figure out what the half-life is by just graphing how long it took for that sample to cut in half. So if my initial sample was 10,000 grams, how long did it take it to become 5,000 grams? That's one half-life. And for this instance, it looks like it's about 6 hours. And so then how long would it take it to cut in half again by 12, it would take 12 hours for it to go through 2 half-lives. So you can just graph the amounts that you have of the sample and then just look to see how long it takes it to cut in half. And that'll tell you the half-life. So by predicting the extent of radioactive decay, you can solve some basic problems. A patient receives 10 nanograms of a radioisotope with a half-life of 12 hours. So they start with 10 nanograms. It has a half-life of 12 hours. How much will remain in the body after 2 days, assuming radioactive decay is the only path for removal of that isotope? So the only way it's going to go away or break down is through radioactive decay. And you can actually calculate N, which is the number of half-lives that have elapsed, using the half-life as a conversion factor. So it's taken 2 days, and one half-life is half a day. So you've gone through a total of 4 half-lives. So you just cut that sample in half 4 times. So then 10 to 5 to 2.5, 2.5 to 1.3, 1.3 to 0.63. So that's how you can just simply figure out how much remains after 4 half-lives. And you can keep breaking it down depending upon time. Radiocarbon dating, we're going to do some practice problems with calculating half-lives during class. Radiocarbon dating is very useful for us in sense of biology, in the biology world. It's the estimation of the age of objects through the measurement of the isotopic ratios of carbon. There's always a little bit of carbon-14 in the air that your body is taking in, and so all of the macromolecules are going to have carbon-12 and carbon-14 within them. And at death, you stop obviously making carbon-12 and carbon-14 molecules. Well, the carbon-12 doesn't decompose, so at death and then, however long after that, your carbon-12 number is not going to change. But the carbon-14 number will, because carbon-14 is radioactive and it will decompose. So you can look at how much it initially had and then compare that to how much carbon-14 is left, because these are going to be the same amounts in the beginning. Then you look at how much carbon-14 is left, and you can determine how old something is, how many half-lives it's gone through, which is kind of cool. So living systems are continually taking in carbon. The ratio of carbon-14 to carbon-12 stays constant during the lifetime. Once the living system dies, the uptake of the carbon isotope ceases, and then the amount of carbon-14 decreases according to this reaction. So it's going to decompose by giving off beta particles, so it's going to go through beta radiation into nitrogen-14. So you just see how much carbon-14 is left compared to how much was in the beginning, and that'll tell you how long it's been decomposing. Now, there are some limitations to it. Because the half-life of carbon-14 is 5,730 years, it does allow us to calculate ages of artifacts, but it's only limited to things that are less than 50,000 years old, which is about 9 half-lives. Things that are older than that, we cannot use carbon-14 to get an accurate depiction of how old the object is. We have to use other radioactive isotopes like uranium at that point, ones that have longer half-lives for us to be able to tell how old something is. So like I said, we're going to do some practice problems in class calculating half-life. You've done this in biology, but we're going to go through radioactive half-life.